This video is going to cover Chapter 6, Section 1, and we're going to talk about perpendicular and angle bisectors. Now, we actually have already talked about perpendicular bisectors back in Chapter 3, Section 5. So first, let's go ahead and review what a perpendicular bisector is, what the definition. And a perpendicular bisector is going to be a segment, a ray, a line, or a plane that is going to be perpendicular to a segment at its midpoint. So remember, what this perpendicular bisector is bisecting must be a segment because it's going to make it into two congruent segments. So in this picture, CP is going to be the perpendicular bisector of segment AB. Notice what we're going to look for is this right angle, indicating that, number one, that it's perpendicular, and another thing that we'll look for is that it splits segment AB into two congruent segments. Now, one thing that we need to pay attention to is the definition of this word equidistant, because we're going to need that when we learn the perpendicular bisector theorem on the next slide. So the word equidistant just means that it's the same distance or an equal distance. So let's go ahead and take a look at what the perpendicular bisector theorem is. In the perpendicular bisector, it states that in a plane, if a point lies on the perpendicular bisector of a segment, then the point is, here's that word, equidistant from the endpoints of the segment. So here, my segment that's being bisected is segment AB, and we can see that point C is on the perpendicular bisector, which is CP. And because it's being bisected, we can see that C is going to be equidistant from the endpoints of the segment. So here, if CP is the perpendicular bisector of AB, then that tells me that CA is congruent to CB. And notice I added congruency marks to those two segments, indicating that they are the same distance. Now, if I added another point that was also located on the perpendicular bisector, and let's say I call this point D, I could put it here. And then if I draw the segments straight to the endpoints of the segment, I know that these segments that I just drew from D to A and D to B are also going to be congruent because of my perpendicular bisector theorem. So if a point lies on the perpendicular bisector, so D is on the perpendicular bisector, which is CP, then I know that that point D is going to be the same distance to each of those endpoints. So the endpoints were A and B, so D is the same distance from A to D as well as B to D. So this tells me that AD would be equal to BD, or it would be congruent. Next, what we're going to do is talk about the converse of the perpendicular bisector theorem. Remember, the converse is going to switch the if and the then. So what this one states that in a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So here, in reverse, if, now they're telling us that the point that's on the perpendicular bisector, it's going to form equidistant, then we know that point D is that it does lie on the perpendicular bisector of AB. So remember, this bisector, notice the arrow indicates that this is a line and it keeps going. So we can see that D is on that perpendicular bisector. So they gave us that AD and DB were congruent. So because they are both the same distance from the endpoints, this tells me that point D is on the perpendicular bisector. And again, I can tell it's perpendicular. I can see my right angle here. And again, I can also see that A to P is the same distance as B to P. I could also draw segments from C to B and C to A. Again, C is on the perpendicular bisector, so I know it is equidistant from the endpoints. Now, different things that I can say about this picture. I could state that C lies on the perpendicular bisector of AB, because again, C is equidistant from A and B. I could also change the point and say that D also lies on the perpendicular bisector of AB. And the reason why I can state this is because of this converse, because I can see the congruency marks here. And I can see that point D is the same distance from both endpoints. I could also say that P also lies on the perpendicular bisector, because again, notice the congruency marks right here indicating that point P is the same distance from A and B. And then lastly, I could also state from this picture that CP is the perpendicular bisector of AB. And I can state that because of the right angle that's there, and I could also see that it's equidistant from the endpoints. Let's go ahead and do some examples using both the theorem and its converse. So the first one, I'm actually going to use the perpendicular bisector theorem. So here they're telling me that BD is the perpendicular bisector of AC. It wants me to find the length of AD. So here, let me go ahead and switch some colors. I know it's kind of hard to see with the green. So here, if point D is on that perpendicular bisector, then I know that the length of CD is equal or equidistant from point D. It's equal to segment AD. So I can go ahead and set these two equal to each other. So I'm going to say that AD, let me do it in white so it shows up a little better. AD is equidistant to CD. So I'll go ahead and set 5x equal to 3x plus 14. Subtract the 3x. 2x equals 14. Divide by 2. And x equals 7. Now, the question did not ask me to find x. It wanted me to find the length of AD. So now I need to plug it in. So AD was equal to 5x. Plug in 7 for x. 5 times 7. And the length of AD is 35. Now, if you were to plug that into CD, remember these are equidistant. So I would get the exact same answer. So if they switched it and said find CD, I could do the same thing. 3 times 7. 3 times 7 plus 14. 21 plus 14. And I still get 35. Because again, because point D lies on the perpendicular bisector of BD, I know that point D is the same distance to both endpoints. So it's the same distance to C as it is to A. Let's try another one. So example 2. For the first two, I'm going to be using the theorem, and for the third one, I'm going to use the converse. So here it's again giving me that ZX is the perpendicular bisector of XY. It's also giving me the length of YZ, telling me it's 13.75. Now, by using the perpendicular bisector theorem, remember if a point lies on the perpendicular bisector, and here's point Z, and it's on the perpendicular bisector, which was given to me, which is ZX, then I know that point Z is going to be equidistant from these two endpoints, W and Y. So if this side is 13.75, then WZ is also congruent, so it also equals 13.75. So the length of WZ is 13.75 by using the perpendicular bisector theorem. Let's try the next one. Now this time, we're not going to use the same numbers here. So what we can do is pretend like this 1375 is gone. Now what they're doing is giving me expressions for the length of WZ and of YZ. So they're telling me that, again, ZX is the perpendicular bisector of WY. So again, I still know that those two segments are congruent. So I'm going to go ahead and set this side equal to its expression, which is 4n minus 13. And then the other segment, YZ, is n plus 17. I'm using the perpendicular bisector theorem, and because I know that these two sides are congruent, my equation that I'm going to solve is going to be, what I'm doing is setting WZ equal to YZ. And again, WZ was 4n minus 13, YZ was n plus 17. I'm going to solve for n, so I'm going to subtract n. I get 3n minus 13 equals 17. Add the 13. I'm going to switch colors here so it shows up. So 3n equals 30. Divide by 3, and n equals 10. Now again, they did not ask me to find just n. They wanted me to find YZ. So now I'm going to go back. YZ was equal to n plus 17. So I'm going to replace n with a 10. I'm going to add it to 17. And YZ equals 27. Now for the third one here, this is where I'm going to use the converse, because this time they're not telling me that ZX is the perpendicular bisector. They're telling me that WZ, let me go ahead now. Now I'm not using the red anymore. So now I'm going to go ahead and label what they're giving me in blue. So they told me that WZ is equal to 20.5. And they told me that WY, this bottom piece down here, is 14.8. They also told me that YZ equals 20.5. So now when we use the converse of the perpendicular bisector theorem, because, so this would be my explanation for number 3. Now, if they just ask you to solve it, all we're going to do is divide 14.8 by 2. But if they ever ask you to explain, so you would say you would be using the perpendicular bisector theorem converse. And because we were given that WZ was equal to YZ, because they told me that both of these were 20.5. So because this, and because we also see that W or ZX is perpendicular to WY, I could tell that ZX is the perpendicular bisector. So what we're doing here is if this, then we can conclude that ZX is the perpendicular bisector of WY. So because it's been bisected WY, and because WY equals 14.8, what we're going to do to solve this is we could say that 2 times WX is equal to WY. So then we could do 2WX equals 14.8, divide by 2. And the length of WX, which is what they were asking us to find, is going to be 7.4. So if they do not ask you to explain, and if you realize that this segment over here, WY, was split into two congruent pieces because X is on that perpendicular bisector, and I know X will be equidistant from W as it is from Y, all I had to do was take 14.8 divided by 2, and that gives me my answer, 7.4. So that is how three examples, 2 using the theorem and the third one using the converse. So next we're going to talk about angle bisector theorem. So the angle bisector theorem states if a point is on the bisector of an angle, then it's equidistant from the two sides of the angle. So again, remember the word equidistant means the same distance. So again, remember back from our previous chapter, the distance is always going to be indicated as with a right angle. Remember, it's always the perpendicular segment. If you remember back when I talked about the banks of the river and you want to swim across this alligator-infested water, you're always going to swim the perpendicular distance because it's shorter than trying to swim from here, say, to here. So remember, the distance is always going to be indicated by a right angle. So that's what we need to look for. So here what it states is if AD bisects angle BAC, so BAC is over here, and DB is perpendicular AB, and DC is perpendicular to AC, then I know that DB here is congruent or equal to DC. So if you have an angle that's been bisected, and we're going to look for the congruency marks here, then we know that this point D is going to be equidistant to the sides of this angle. So let's go ahead and look at the converse, and then we'll do some examples. So again, the converse is going to flip the if and the then. So now it states if a point is in the interior of an angle and is equidistant from the sides of an angle, then it lies on the bisector of the angle. So again, what we're looking for is that we have the congruency marks here on these segments and that they're also perpendicular. So we'll be looking for the right angle. So here, if DB is perpendicular to AB and if DC is perpendicular to AC, then that tells me that DB, and we're given that DB and DC are congruent, then we know that this ray here, AD, is bisecting this angle here of BAC. So then we can say that this angle is congruent to this angle. Let's try some examples. So it wants me to find the value of X. What I'm going to use here to find the value of X, I'm using the angle bisector theorem. So what I'm going to look for is notice that I'm given that I have two congruent angles here. So I know that this angle here has been bisected. I also have the right angle marking that this is a distance. So then I know that because this angle has been bisected, I know that these two distances are equal. So X would equal 15. Try another example. This one's going to use the converse. So for this one, we're going to use the converse of the angle bisector theorem. Notice this time they gave us that the distances were equal, that they were equidistant, and we know that they're a distance because of the right angle. So because we're given that, we now know that this angle has been bisected and this angle is congruent to this one. So in order to solve this, I'm going to set these two expressions equal to each other. So I can set 4x minus 6 equal to 3x plus 5. Doesn't matter how you write this, you could have written the 3x plus 5 first. I'm going to solve for x, so I'm going to subtract 3x from both sides. I get x minus 6 equals 5, add 6, and x equals 11. Now it did not ask me to find any lengths here. I don't have any letters here, so all it asked for was x, so I'm done. Try another one. So this time they're giving us that the angle has been bisected. So now I can use just the angle bisector theorem, not the converse this time. So because the angle has been bisected, I know this segment is congruent to this. So that's my equation I'm going to solve. 5x equals 6x minus 5. Okay, so let's go ahead and solve for x. Let me move the 6x over. Now I could have written 6x minus 5 on the left. It doesn't matter. And then I get negative 1x equals negative 5. Divide both sides by negative 1. I don't want a negative variable. And x equals 5. It did not ask me to find the length of anything. But let's change this one up a little. Let's say if I had an A, a B, and a C here. And let's say instead the question said, find the length of AB. Then we would have taken what AB equals, the 5x, plug in the x we just found, and the length of AB would have been 25. The length of BC would have been exactly the same. Because again, remember, point B is equidistant from the sides of that angle. All right, now the next example, we actually did this in lesson 3.5. These were the very long problems that I told you I would not test you on, that I would break it apart and just ask you to write equations of perpendicular lines. Now we actually have to come up with the equation for the perpendicular bisector. And again, we did this exact same question in the homework. I believe it was number 10 in your 3-5 homework. So now we're going to do it exactly the same thing again. And we're going to follow 4 different steps. So the first thing you're going to want to try to do is graph the segment PQ. Now, it's already graphed for you here. PQ is actually the blue segment here. So let me go ahead and add in these endpoints that are written here. So this is endpoint, the Q is endpoint 4, 1, and P is the endpoint -2, +3. So the next thing I want to do is find the midpoint. Well, obviously, if you're given a picture like this, we already see the midpoint's already labeled for us. It's this order pair 1, 2. But I'm going to do the calculation because you're not going to be given a graph. You're going to have to do the calculations. Okay, so my next step after I graph this is to find the midpoint of PQ. And again, if you're not given a graph, you have to use your midpoint formula. So the midpoint formula, remember, is x1 plus x2 divided by 2, y1 plus y2 divided by 2. So -2 plus 4 divided by 2, and 3 plus 1 divided by 2. So this will give me 2 over 2, and then 4 over 2. I can now simplify this, and my midpoint is equal to the order pair 1, 2, which I already saw was already there, the point of intersection. The next thing I need to do, my next step, is going to be to find the slope of the perpendicular bisector. So the first thing I want to do is find the slope of PQ. And then back in chapter 3, we learned that the perpendicular slope was always opposite reciprocal. So I'm going to do the slope formula using points P and Q. Remember, slope formula is y2 minus y1 divided by x2 minus x1. So let me go ahead and calculate the slope here. So 1 minus 3, 4 minus -2, -2 over 6. And the slope of PQ is going to be 1/3. However, I don't need to use that slope in my equation. I need to turn that slope for my perpendicular bisector into the opposite reciprocal. So the perpendicular bisector slope is actually equal to positive 3 over 1, or just positive 3. And then finally, my fourth step is going to be to write the equation. So I'm using my newly found slope, and then I'm going to use one of the ordered pairs. I'm going to go ahead and, or actually I have to use the midpoint. So I'm going to be using the slope that I just found, and I'm going to be using the midpoint, which was the ordered pair 1, 2. I'm going to plug it into y equals mx plus b. Now you could have also plugged it into point slope. That works as well. So remember, this is x, this is y, and then this was your m. Remember, we're solving for b first. So I'm going to plug in 2 equals 3 times 1 plus b. 2 equals 3 plus b. I'm going to subtract 3. And my y-intercept of my perpendicular bisector equation is going to be -1. So now I'm going to take that newly found y-intercept and my slope and then plug them both back in to y equals mx plus b. So my equation for my perpendicular bisector is 3x minus 1. Again, we did exactly the same type of question back in chapter 3. So again, this is a review. This time, more than likely, you may have to do all of these steps on your quiz or your test. So that is it for section 6.1. And then tomorrow I'll take any questions you have.